Welcome everyone. This is Women Who Code Python. Our mission is a global nonprofit dedicated to inspire women to excel in technology careers. Our main goals are to empower with skills needed for professional achievement, educate companies to better promote, retain, and hire talented women, build a global community where networking and mentorship is valued, develop role models, and support this generation of engineers. We have a code of conduct, and we are an inclusive community. So anyone who supports our mission is welcome. We do have this code of conduct to our members to follow. To learn more, you can visit womenwhocode.com/code of conduct. We have different tracks, online tracks that everyone is able to access if they're interested in. We have front end, we have blockchain, we have Python, which is us, mobile, cloud, and data science. We want to thank our sponsors, the Home Depot and Atlassian. Many thanks for them to support the track community to be able to have possible this event. Looks like this got stuck. Just a second. You can also get involved if you're interested. You can go to womenwhocode.com/Python. We are always looking for leads and evangelists. You can as well join the conversation if you're interested. We have different online Instagram. We also have Twitter and we have LinkedIn. If you scan those in, or if you want more information, is www.codepython. So we're talking tonight about fuzzy search algorithms. We are going to introduce our speaker for tonight. Is Jiaqi. She's a lead software engineer at the Center for Transactional Data Science at the University of Chicago. Previously, she was a tech lead at the Button and data scientist at Capital One Labs. She's passionate about bridging the gap between the science and engineering part, data-driven work, and champions inclusive in the workplace, and advocates for culture where everyone input matters. She's also an active Write, Speak, Code, and Women Who Code Python communities. So I'm going to pass it up to you.
Okay, thank you. Okay, great. Yeah, so I'm Jiaqi. Welcome to my talk on fuzzy search algorithms. I'm really excited to be giving this talk as part of Women Who Code Python. If you do have questions, feel free to put them in the chat as we go. I will try my best to address them in real time, but if not, we will get to them at the end. Who am I? As mentioned, I was previously a data scientist, and I worked a lot in data engineering. Now I'm Chicago-based, and I mostly work on backend services, and my primary language that I develop in is still Python. So I had originally given this talk as part of PyCon a few years ago on fuzzy search algorithms. And in my GitHub, there's actually a Jupyter notebook with a lot of the code that I'm going to be referencing today. So feel free to check that out. I have also pasted it into the chat. Cool. So what are fuzzy search algorithms? In this particular talk, I'll cover a couple of different approaches to fuzzy search. Fuzzy search is also known as approximate string matching. And it's usually used when, sometimes you don't really know what we're looking for in a search algorithm, or we want to convert speech to text and be able to analyze that. Or for whatever reason, we want to have, words in our data that we have to analyze. So it actually becomes really relevant and important depending on what kind of data sets you're working with. So there's a variety of different algorithms and they have very different approaches. SoundX, which I'll talk a little bit more about, is based off of sounds. Levenstein, which is also known as the distance between words or the edit distance, it's useful for correcting things like typos. The n-gram is a little bit more targeted and draws upon more context. So I'll go more into that. And then last but not least, word2vec. It's more the natural language processing space and is actually a little bit beyond fuzzy search and more towards associating meanings between words. In this talk, all of my examples are going to be in Python. And I have a couple of examples that will reference built-in functionality in the Postgres database. So those are the tools I'll be referencing. Cool. So SoundX is a phonetic algorithm, and it's indexing words based on sound as associated in the English language. So as you can see, we're already starting to have a little bit of limitations with this algorithm here. It's ideal for spelling inconsistencies, and it assigns a special encoding, which I will show you. So this is the American SoundX encoding, and these letters are sort of assigned these numbers. Vowels are ignored. The letter H, W, and Y are also ignored. And then the other letters are sort of assigned to these numerical values, and it basically converts a word into a letter and then also some numerical value. So we will take a look at that with this Python library called Jellyfish. So if you run the SoundX algorithm over that, over the word Washington, it's assigned to the number 252. And then there's a letter that it starts with that it is also associated with. So that becomes the SoundX encoding for this particular string. So if I have a typo and I, replace the letter A in Washington with the letter U, the pronunciation is more or less still the same and it sounds the same. So the encoding actually is still the same. So use cases, abbreviations are useful for using SoundX to analyze. Typically, abbreviations still might try to preserve the sound of a word if if the abbreviation is of the original word as opposed to abbreviation that is based off of a couple of different words. So LGA has a similar SoundX encoding to LaGuardia. Non-numerical characters attached to words. So I used to work for a credit card company and we would get transactions with a lot of jargon or extra characters attached to the name of the merchant. So being able to associate something that is actually the same entity, but might have some garbage characters attached, using the SoundX algorithm is useful for that as well, because these extra characters, if they're not pronounceable, might not change the validity of the sound of the word. Words that sort of sound similar might have very similar encodings. So in this case, accept and accept actually has the same numerical value, but start with different letters. Homophones will clearly have the same or very similar sound X values. So it's an interesting way to analyze homophones if you are working on that. Okay, so there's actually a built-in fuzzy string match extension within the Postgres database as well. And within Postgres, you can leverage this SoundX algorithm to actually calculate the difference between different values. It's useful to be able to assign numerical values to words, but ultimately what we're going to want to do is analyze that data, and analyzing it, you have to be able to compare and contrast these words. So here you can calculate sort of the difference between values. So this is sort of just an example of how I was connecting to a Postgres engine and the database itself. And if you run this query, which is calculate the difference between and without an E, you'll get this sort of result. Those are the SoundX values, and that is the difference, which is that it's identical. All 4 characters within the SoundX value are identical. So I had this database of fuzzy names actually when I was running this query, and within this I had various spellings of different cities. So it is able to basically fetch all the similar strings from the search string. And I can specify in this query, get me all the records in this database where the SoundX difference between the record and the string Washington, D.C. is greater than 2. So it's, in my opinion, greater than 2 is a little bit more similar. And here are sort of the results. Obviously, 2 is not as similar in string values as 4. So depending on the constraint there, I would get less results or more results. So this is a pretty cool way to work with the Postgres database and a way to analyze strings. But as you can see, this is not the best result. So the pros of SoundX are, it's pretty easy to implement. As you can see, it is very computationally fast because all the encodings are essentially, hard-coded values. One letter maps to one number, and it's pretty straightforward. But the sort of cons are, it really only works on ASCII characters. So it doesn't really support foreign languages, and specifically the encoding that we went over today only supports the American language. And you're a little bit limited in how you calculate distance between words because there are only really 4 values to compare at the end of the day. So how can you better calculate distance? And that leads to the Levenstein distance, which is also known as the edit distance. And it actually accounts for how many characters you have to change based on the standard keyboard to have the same string. It is also computationally fast because you only have to sort of figure out what characters have changed between 2 words. But you sort of limit yourself to a pairwise comparison, which means you can only compare 2 items at a time. Okay, Levenstein, again, there's a library within Python, and you can calculate the Levenstein distance for Smith with the Y and Smith with the I. The Levenstein distance is 2. There are 2 letters that have to be changed here. The Y has to change to an I, and then there's an extra E at the end for the first string. It does support non-ASCII characters. So basically it supports any kind of characters that you need because it's just calculating where things are different. For a use case that I ran into before, Levenstein was pretty useful in comparing addresses because or it's interesting when comparing addresses because 99 Broadway and 100 Broadway geographically might be next door or across the street from each other. But within a Levenstein distance, because they're numerical values and because those numbers are different characters and they have drastically changed, it has a pretty large Levenstein distance. So this is where, depending on what you are trying to use fuzzy search algorithms for, you sort of have to take with a grain of salt what to do with the comparisons and values that you get. And the other counterexample is 99 Broadway is pretty far from 999 Broadway, but the Levenstein distance is really, really short because there's only one letter or number that has changed. Unlike SoundX, this is a lot more useful for comparing longer strings. So that includes sentences, and you can sort of calculate the distance between those two sentences. Again, the Levenstein distance of the sentence or the string, it doesn't really change because the difference, number of letters you have to change between those two values are the same. It brings up to another point where, again, like string algorithms don't compare the meaning of words. And we'll touch on the meaning of words later on. But that is another aspect that you might have to think about if you're analyzing this kind of data set is, do you really want to compare the strings itself, or are you trying to compare the meaning of the text? There's an extension of Levenstein known as the Damaru-Levenstein algorithm. It is like Levenstein, but accounts for transposition of adjacent characters, which means typically adjacent characters, if they're swapped, in normal Levenstein will be counted as 2 distance edits. But within this other algorithm, which is a little bit of an improvement, they are treated in a special case. So the very common misspelling that I am very guilty of is misspelling receive. And in this case, in the Damaru-Levenstein distance, this is treated as a 1, but in the normal Levenstein algorithm, this would be a 2 because the 2 letters have changed. So this is really helpful, especially when, flipping 2 letters is not always, it's not always as severe as drastically changing the value of the letters. Okay, so this brings me to more complicated algorithms such as the trigram extension. So n-gram is the analyzing the distance or context of words using groupings of letters. So instead of thinking about the difference between 2 words based on each individual letter being different from each other, you take in a lot more context and group the letters as a segment of 1, 2, 3, or any other value of n. Depending on the value of n, this can be very slow to implement or calculate the n-gram for each string. So typically the trigram, which is 3 letters grouped together at a time, is the most popular and most commonly used, as it is efficient in terms of being able to calculate trigrams for a grouping of strings, but also takes in enough context that you can do some really interesting analytical stuff. Okay. So this is an example of how you would calculate an n-gram and specifically a trigram. For those of you who might be familiar with natural language processing, It's pretty common to analyze text within the structure of trigrams. And you can just group in groupings of 3 to get the trigrams you need for analyzing a sentence. So in this case, for the quick brown fox jumped over a lazy dog, you need each 3-word at a time. So the quick brown fox, et cetera, et cetera. And those are your trigrams, and then you can run analysis on top of that. So for women who code, I guess if I wanted to break the n-grams down by character instead of just words, which is what these fuzzy search algorithms will end up doing, this is what it would look like. Okay. And then you can sort of calculate the, I guess, similarity between 2 different trigrams using this algorithm for getting the intersection of the trigrams divided by the union of the trigrams. So this allows you to, this is one way of calculating how similar 2 words are. And this gets a lot more complicated than what SoundX has been doing or what Levenstein has been doing. But this is how ultimately you can end up using things like trigram. Once you are able to break it down into trigrams of characters, you can run more complicated analyses over it. Okay, so within Postgres, there is a extension called Postgres Trigram, and you can leverage it to calculate trigrams as needed. So again, I had some city names stored in a Postgres database, and here are my queries for finding the values that are similar to the city name Washington in the descending order for their trigram similarity scores. And as you can see, this is a much better result than what I had gotten when I used the SoundX search on Postgres and set that value to anything greater than similarity score of 2. So the trigram search is actually a fairly powerful tool. So a couple of things to note for trigram. It looks like it would be great. Wait, so I have a question. Do the trigram n-gram algorithms deal with semantics at all? Would it recognize that girls is similar to women and classify the similarity accordingly? Or is it just focused on the words like the Levenstein algorithm? So that's a really great question. Trigram and n-gram does not deal with semantics. It does not recognize that women and girls are similar in meaning, and it will treat those because they are entirely different letters as separate entities altogether, just like Levenstein would treat them as completely different. I will touch a little bit more on semantics analysis at the end with word to back. So I'm really glad that you asked that. Cool. So couple of things to note. Trigram seems pretty great compared to at least, you know, what we've seen so far with SoundX and Levenstein. But it is really slow to compute your actual trigrams and then run the comparison between them. So it is a lot more computationally heavy than some of the algorithms we've seen so far. And especially if you're running these similarity scores, running this query against a really large table, it can take quite a long time to scan through all the records and their trigrams and calculate all the similarity values. So it's not really ideal for large data sets, but within Postgres, there's these indices you can create that will pre-compute the trigrams for the values in your, for values in your column. And that does sort of speed things up a little bit because those are already pre-computed. So when you run the query, they don't have to compute the trigrams again. So that is one area of optimization, but again, if you're implementing it from scratch or running against Postgres or using a Python library, either for all those scenarios, this is a pretty computationally heavy procedure. Okay, that brings us to the last topic, which is actually one of the more exciting topics, which is semantic similarity. So far we've only looked at sort of, differences in lettering, differences in characters, which is useful in its own way, especially for if you're looking at, again, transcribing text and there might be misspellings, or if you're looking at, scenarios where there might be typos, so like things like autocorrect, or if you have like data that needs to be clean and there's extra characters attached to some strings. But semantic similarity is actually where it gets really interesting. And this is where you can address scenarios where, girls who code and women who code, girls and women are actually quite similar in meaning. So there is something called NLTK, which is this word net. And then there's also word2vec, which is word vectorization. And you can basically convert words into numerical values so that you can run analyses on top of them. So for NLTK, you have a corpus of words. And those that corpus of words, for those words, they have associated values. And then you're able to calculate the similarity between two words based on their associated numerical values built off of the corpus. So in this scenario, blue and green has a value of 0.875, which is quite high because these values, they go from 0 to 1. And they are similar in value, I guess, because they're both colors. Word2vec is a much more statistically heavy computation, and it leverages the relationship between like different words and different symbols. And it's kind of allows for better statistical modeling for leveraging the meaning of the words. Oops. There's a word2vec library in Python. Of course, there's everything library in Python. How is the difference calculated between two values? For word2vec, the difference is it's vector calculating the difference between two vectors, or this is a very large vector, but essentially it's just subtracting or adding these numbers in vector form. You can do a lot more heavy computations as well. So if you're building, I guess, a regression model, you can leverage some of these arrays. Okay, so this is just an example of when you have to sort of build up a corpus for word2vec as well. I used a predefined one with some common words in everyday life, but this is just an example of what the word coffee looks like in this word2vec model. It's a very large, it's essentially converted into a very large array. Next. And then I'm able to, so within word2vec, you can say, give me the top 10 words similar to my current word out of this corpus. And here are the ones that for the specific data set that I was able to pull. Here are the similarities for coffee, those with the highest values. Again, these similarity values go from 0 to 1. So 0.8 is relatively high, but not the highest value you can get. Again, for the word emails, here are some within the corpus that I downloaded that were similar. Okay, so now that you have converted your words into vectors, I think this goes back to the question about how difference is calculated. You can do some kind of arithmetic with them, which is known as like making an analogy, because it is in the practical sense, this is an analogy. So for me, I thought it was really interesting to see this, but breakfast minus morning plus night is dinner. That is in my opinion, the correct value. So I'm really happy to see that that is the top value in this query against the corpus that I was running this on. Yeah, I ran another one, which is sun plus cold minus warm is moon, but also Earth and other planets. But also pretty interesting. And then I don't know if anyone's from San Francisco, but apparently not being able to find lodging is associated with San Francisco in this corpus that I'm running against. And then this is also sort of, I guess, as an analogy, pretty accurate. If you take a hotel minus the lodging part, but add food, that's restaurant as another service industry. Cool, that's sort of it. I have a couple of resources in these slides. Somebody had earlier asked, are the slides available to look at after the lecture? I think it's probably okay. I'll probably share them in the Python, the Women Who Code Python Slack. So happy to share these slides. And also the GitHub link that I referenced has all the code snippets around everything that I showed today. So the fuzzy search documentation on Postgres, the Levenstein library I use, Jellyfish, and some of the other libraries I use are referenced here as well. That is it for my talk. Anyone have any other questions? Okay, where did you get the corpus that you used for the Word2Vec examples? There was a Word2Vec tutorial online that I had initially looked at when I gave this talk at PyCon. So that should also be referenced in the GitHub repo, and if not, I can follow up on Slack. There's probably more recent material for Word2Vec that could be interesting too. Going back to SoundX, does it only capture the first 4 letters in the hash? What if it's a very long word? It doesn't capture only the first 4 letters, but I think it's, depending on the algorithm, it might select the letters that it thinks are most significant. What happens if it's a really large word? I do think that for SoundX, because it truncates into those 3 numerical values and 1 letter, if it's a long word, then you're definitely going to sacrifice accuracy there and you're going to lose some data. SoundX is a really fun algorithm to play with, but it's not the most viable depending on the use case that you are working with. How did you get started in becoming a data scientist and coding? I got into data science as one of my first roles out of school. I had the opportunity to work on, both learning about data science and bringing data science like mentality and new tools to the company, but also developing products using data that actually benefited consumers. And it was really interesting for me to, I guess, both dive into data science best practices, but also figure out how to translate some of the research that was being done in data and machine learning into like customer experiences. What are some unexpected real world applications of Word2Vec? I don't really have the best answer for this. I don't currently work in NLP right now. So it would be interesting to learn about unexpected real world applications. So I suggest, I guess if you're really interested, to do more research online on that. I unfortunately don't know. After intro to Python, what is the next language? I think that really depends on what you're most interested in. For a field like data and data science, Python is kind of what everyone's using right now. R is also really popular within data science, but it really depends on what you want to do in terms of the software engineering or data science field. Python can be used for a lot of different things, but if you're doing more, API stuff, Python, Java, Go, and stuff would be good too. What's a good corpus word count size as a general rule of thumb? I think that really does depend on what you are working with. Obviously, the larger the corpus, the better, but there can be limitations. I don't have a general rule of thumb there, but it really depends on what kind of, what your use case is and what kind of data you're analyzing. How to increase the speed in matching while matching 10 million names versus 50 million names. So matching speed really, again, depends on the algorithm you're using, depends on the implementation of the algorithm. I would say that in my experience, I've had to build some of these fuzzy search algorithms in real time, and sometimes you just can't get around the computational speed, and you probably at that point, you're going to have to implement a cache and then allow the cache to help you meet whatever matching speed you are required to do so. So that's kind of my advice on speed, is sometimes it's out of your control and it's better to just leverage like a caching mechanism or something. What's the most interesting project you worked on using these resources? I guess I would say that the address example that I pulled out is from something I worked on in the past, and I found that really interesting. But for addresses specifically, there's actually there's obviously a database of known addresses, at least within the United States, and you can compare against that. So you don't actually need these algorithms, but that is something that I've had to work with, and validating that addresses are correct. Would you recommend SQL? So the examples I had here for Postgres were all in SQL syntax, even though I have run them through a Python because I was hitting the database using a Python library. So I do recommend SQL. Does SoundX work for non-American spellings? I think it is possible if you have encoding, the encoding mapping for non-American spellings, but the algorithm that I was referencing is specifically the American SoundX encoding. Does the size of encoding depend on something, or is there a general rule to choose its size? Coffee had a very large encoding vector. So again, that depends on the model that you're running. I had used a library that generated it on my behalf. Researchers will sometimes write their own. So it just depends on the model, just the model that the corpus has run through. Oh, and then again, the question on, so fuzzy string matching can take a lot of time, especially organizational matching. Yes, so string matching does take quite a lot of time. I think it does depend on, if you're building a data pipeline, you might just have to wait for the results of the string matching. But I think, as mentioned earlier, if once you get those results, caching them so that you don't have to recompute them every time is really helpful. Okay, I need to build a list of acronyms and their definitions in a huge document, and then eliminate any redundant notation after the first defined string instance of the acronym. Which of these methods would best generate an efficient fuzzy search, if any? That's a great question. I've also worked with acronyms. It depends on if those acronyms are more phonetic or just abbreviations. I would say that in my case, I ended up using Trigram for acronyms because they were quite, it was a little bit easier to sort of gauge the acronyms that matched on different trigrams. But if they are pure abbreviations, it might actually be really challenging to use like fuzzy search algorithms because acronyms can get shortened. So for instance, if you're working like NASA is an abbreviation acronym, but you wouldn't be able to match it very well using these fuzzy search algorithms against the full like composition of NASA. So that might be just something that you have to build and map. Any recommendations for someone starting out in data engineering? I have a lot of recommendations, but I think what has helped me is just, doing various things, making sure you're still like hands-on in implementing data pipelines or streaming processes, whatever it is that you are working on. And I have also enjoyed reading some of the blog posts out there from companies who do data engineering really well. So such as Netflix has a really great data engineering blog. So does Airbnb and Spotify. So learning from people who have gone through some of these technical challenges has always been helpful. Cool.
Awesome. Well, thank you for joining us and providing this information. Like we said, we already shared the she already shared the GitHub, and if you can share with them in Slack the presentation, that would be helpful.
Yeah, I can definitely. I'll share this presentation in Slack as well.
Awesome. Thank you very much. Thank you everyone for attending tonight.